Okay, so today we are going to start with the idea of basic derivative. Before we initiate the processes, let us firstly have a look what does derivative mean. In physics, I believe you have already started the application, right?
Yes,
Yes.
sir.
So, in terms of derivative, when we try to have rate of change, basically for the curves, okay, we know that rate of change for a straight line is actually the change in ordinate by change in abscissa. Doesn't matter for how long span you are considering that, it's going to stay the same, as straight lines are the curves which doesn't change directions, right? So if we do have a straight line, in that case it does not change its direction, and hence it doesn't matter how far we select 2 points x1 comma y1 and x2 comma y2, the rate of change y2 minus y1 divided by x2 minus x1, that will always be tan theta for constant inclination theta. Now when we look into the curves, they are not always like the straight line, they keep on changing their direction. So for curves, the decision on rate of change is instantaneous. Like from the curve, if we select a very small part, as you can identify, we are considering the y is equals to f of x curve, which has been drawn in green color. Now from that curve, we are selecting a very small part. And how we are ensuring that is very small? The abscissa for the first point been taken x and corresponding ordinate been found fx. For this second point, we have considered the abscissa to be x plus a, the corresponding ordinate been found as f of x plus h. Okay. Now, if we ensure that h is something very small, then we can ensure that the span we are considering is something very small. For a very small part taken from a curve, we can treat it like a straight line, and hence the rate of change for this specific portion can be marked as change in ordinate divided by change in abscissa. And to ensure that the span is very small, we have considered h approaching to 0. Okay. With this idea, what representation we get, that is called first principle of derivative. As per first principle of derivative, for any function y is equals to f of x, its rate of change with respect to x is the limiting value for h approaching to 0, and we calculate the limit for change in ordinate divided by change in abscissa. We also mark this particular expression as f dash of x, and if we consider it is as y is equals to fx, then we can also mark it dy by dx, which is also same as d by dx operator operating on y. D is actually rate of change operator. When we write d by dx, so that means we are searching rate of change with respect to rate of change of x. And if this operator operating on y, that means at this moment we are trying to have rate of change of ordinate with respect to rate of change of axis. Now, this small section we have selected from the curve if we consider to which line it is actually coinciding to, then we can identify for any instantaneous small part taken from a curve, if it is treatable like a straight line, then it always coincides with the tangent to the curve at that very point. Is it okay with all? Now, ahead of this, we will go for derivatives of some frequently used basic functions. Like this is the list where we will get to some primary functions and their reference rate of change. So the first column we are using is for the function, and if we find their rate of change with respect to rate of change of x, that is, if we apply d by dx operator on these functions of x, so what we will get as dy dx or f dash x, that's been written on the right column. So over here, as you can find, sin x after rate of change, it's giving cos x. So on the curve of y is equals to sin x, if you try to get the rate of change of ordinate with respect to rate of change of x, that is the variable independent variable angle and the independent variable, in that case at that very point we will get the rate of change same as cos of the same angle. When we apply this operator on cos, we will get minus sign of that same variable angle. Okay, so though I believe all of you have used this results for physics or some other required field where you need to apply derivative, but what you will try to identify from this table is not only the result, but when we are having a differentiation with respect to the variable angle, then we will keep in mind the first reference as sine changes to cos when differentiated with respect to the variable angle. So if it would have been sine theta, then d by d theta would have been cos theta. If it is sine of x square plus x, then rate of change with respect to rate of change of x square plus x will be cos of x square plus x. So if sine is differentiated with respect to the variable angle, then it generates the rate of change cos of that very variable angle. Similarly, when cos is differentiated with respect to the variable angle, it's minus sine of that very variable angle. Similarly, tan changes to sec square, cosec change to minus cosec into cot. The angles are remaining the same as the variable angle with respect to which we are performing this rate of change. For sec, it will be changed into sec into tan. For cot, it will be minus cosec. So the first six of this list is the basic six trigonometric operation and reference of their first order derivatives. The next reference is algebra. X is the variable and we will believe the power n is constant, and hence this algebraic reference x to the power n will provide rate of change n into x to the power n minus. So through the algebraic rate of change transformation, we can identify the differentiation algebraically resulting in reduction of degree. As such, it is also a reduction in dimension. Like you have already gone through from displacement to velocity, velocity to acceleration. where displacement is appear with dimension L, that is standing for length, whereas velocity is L per unit time or length per unit time can be written as L t to the power minus 1. When from velocity we move to acceleration, over there we get to L t to the power minus 2. The next reference is a to the power x, that's the exponential reference, and in that case the derivative will be a to the power x into natural log of a. ln stands for log with respect to base Euler number e. So this is called natural log, also represented as ln. And if we are considering a to the power x, you should believe a is something positive. As within the function, we have already considered that exponential functions with negative base, their existence and non-existence are so frequent, we cannot treat them properly. Okay. So if we are treating with some a to the power x, then the reference of the derivative will be a to the power x into natural log of the base. And as per our consideration, a being positive, log of this positive base a is not at all problematic. The last reference is for logarithmic form, and it gives you, if we have rate of change of natural logarithm with respect to its variable index number, the rate of change will be reciprocal of the index. Is it okay to all?
Yes, sir.
So after the completion of this basic derivative list, let us have some of the establishment that how from the function we are getting this rate of changes using the first principle. I'm starting with the very first row, that is when f of x was sine of x. So for d by dx applied on sine x, using first principle, it is the limiting value of sine of x plus h minus sine x divided by h, for h being very small approaching to 0. Now as per the concepts of limit, we will try to have this format decisive whenever we can get something sine of h by h form. And in order to have that, this difference is not much preferable. So we would like to have it factorized first. So sine of x plus h minus sine x, this can be factorized into twice cos of average of the two angles multiplied with sine of half of the difference of the two angles. The denominator been kept the same. Okay. Now we have kept the cosine term as it is, but on a simplified note, this section became sine of h by 2, and to correspond that, we brought this 2 in the denominator of h and made it h by 2. As per the identities of limit, this marked section is now following the identity of standard form, h approaching to 0, sine of h by 2 divided by h by 2. We do have a limiting standard reference for this ratio, which is 1. And if we split this section using algebra of limit, then substituting h equals to 0, from this section, we can manage to have cos x for ourselves, and this portion is generating limiting value 1. So it shows how from the function sin x, we are generating the rate of change as cos of x. Is this part okay to all?
Yes, sir.
I am showing you another variation where the function is not a direct and simple variation. Over here, we are considering association of two types of function. But when we are following the first principle, even this should not create any difference. So if we believe f of x is product of algebraic function x with trigonometric function sin x, following the first principle, the rate of change of fx with respect to rate of change of x, that is f dash x, will be limiting value for h approaching to 0 applied on x plus h into sine of x plus h minus x into sine x whole divided by h. For simplification purpose, we will firstly split this section. From here, we can get it splitted as x times sine of x plus h, and we will also get another term h times sine of x plus h. Now, after the splitting, we will bring these pink highlighted sections together. And if I split this ratio, the h can be cancelled out as h approaching to 0, but it is not exactly 0. In that case, this portion is not creating any problem as far as limiting value substitution is concerned after the cancellation. So we have segregated this section after cancellation of h. For the pink highlighted section, we have kept the x common, and the sine x plus h minus sine x can again be factorized like the earlier form into twice cos of average of the two angles multiplied with sine of half of the difference of the two angles. And in a similar approach, we will again bring back this 2 in the diameter in the denominator of h, and hence will create the standard reference of limit. The rest portion is again not problematic under limit. So after splitting the limit into two sections about this product and substituting h equals to 0 other than the reference identity, we can manage to have the final result for rate of change as sin x plus x cos x. Now, ahead of these examples of first principle based application, let's just have a look over the algebra of derivative. The first algebra of
Sir,
derivative,
can you
it
scroll
says,
up again?
I'll show that later. Algebra of derivative, the first point says that differentiation is commutative with constant multiplication. So the left hand side, it shows a constant multiplication of a function when differentiated with respect to x gives you the same result when you are firstly differentiating the function and then multiplying c. The second point of algebra, it says differentiation is distributive over addition or subtraction. So as per left hand side, you add two functions fx or gx, or you perform a subtraction of the two and then perform the derivative, will give you same result as their individual derivatives are getting added or subtracted. The third point of algebra, it says if you differentiate product of two functions, then it will be first function unchanged multiplied with derivative of the second function plus second function unchanged derivative of the first function. So first two algebras are quite trivial. The commutativity with constant multiplication and the distributive nature about addition or subtraction. But product onward, we need to treat it in a bit different. So I'm repeating again, product of two functions when differentiated, the result of the derivative will be first function unchanged, derivative of the second, plus second function unchanged multiplied with derivative of the first. And finally, if we think of derivative for a ratio of two functions, it will be the new denominator as square of the old denominator, and in the differential result, the numerator will be old denominator multiplied with derivative of actual numerator minus numerator unchanged derivative of the denominator. Okay. So for fx by gx, the derivative with respect to x is gx unchanged multiplied with derivative of fx minus fx unchanged multiplied with derivative of gx, and this whole thing will be divided by square of gx.